Okay, let us begin. Hello, everyone. My name is Anton Rodomanov, and I will be giving the first lecture today. So this will be the lecture on stochastic optimization, and it will consist of two parts. So let us start with the question, what is stochastic optimization? So stochastic optimization, first of all, it's just still optimization. So we're going to solve some optimization problem where we're given some function. And for simplicity, in today's talk, we're going to consider only unconstrained optimization, but actually everything can be generalized to constrained optimization as well. So what differs stochastic optimization from ordinary optimization is our main assumption. In classical optimization, we assume that we can compute exact values of our function and its exact gradients, etc. But in stochastic optimization, we assume that it is simply not possible. And in a minute, we'll see several examples why this may not be possible. But our goal is to solve somehow this problem by having access only to some stochastic unbiased estimates of these quantities. And this is formalized usually with the notion of something which is called stochastic oracle. And stochastic oracle, this is some device which, given some input point x, returns us some random vector, which is called stochastic gradient. And the most important property of this vector is that it is unbiased. So the expectation of this g of x equals the true gradient. Actually, we may consider also stochastic oracles which return unbiased estimates of the function value, maybe Hessian and so on. But actually, this is the most popular kind of stochastic oracle, and this is already very useful, as we'll see. So in this talk, we are going to assume that the stochastic oracle returns only gradients. So again, these are not true gradients. These are some random vectors, and their expectation equals the true gradient. Actually, we will see that this assumption alone is not enough for solving the general stochastic optimization problem. And it is quite evident that we also need somehow to bound the fluctuations or the variations of this stochastic gradient. Because if it fluctuates arbitrarily, if its fluctuations are arbitrarily large, then we can do nothing. So what is our goal? Our goal is to somehow solve this problem by having access only to this stochastic oracle. Now let us consider two main, I would say, examples which arise frequently in machine learning and related to stochastic optimization. The first example is the most classical one, and it is called stochastic programming. In this case, our objective function, which we are going to minimize, is giving us some expectation of some family of functions. So xi is a random variable, and we take the expectation with respect to this xi. So expectation, as we all know, this is some integral, and p is the distribution of this xi. So what are the two problems that we may encounter when we are going to solve this problem? First problem is that actually this distribution of xi is often unknown. So we simply not know it. We know that it exists, but we do not know the exact distribution. And you all know that this happens frequently in machine learning. So actually, in machine learning, our goal is to find out this true distribution. So this is the first problem. We simply cannot compute this function value and also its gradient because we do not know this distribution. And the second problem is that even if we know this distribution in some problems, then we see that here we have some multidimensional integral whose dimension is the dimension of this random variable xi. And usually these integrals are simply intractable because if we are going to compute it, we need to use some numerical methods, and these numerical methods for integration, they usually need for obtaining an epsilon approximation of our objective function, they need exponentially many operations in the size of this random variable xi. So this is usually not possible for d greater than 5, 10, something like this. However, we know that if we compute the gradient of this function under some mild assumptions, we can interchange the integration and differentiation. So we obtain this formula, and this formula provides us a simple way to generating a stochastic gradient for this function. Indeed, in such problems, as I already said, even if the distribution P is not known, like in machine learning, what we usually have, we have samples from this distribution. And in the second case, we also, in many cases, we can efficiently sample from this distribution. Because if we are talking about some randomness here, some random variables, they need to come from somewhere, right? And so this formula provides us with a formula with at least one stochastic oracle for this kind of problem. And this stochastic oracle is simply given some point. It generates a new random variable, xi, independently, and returns the gradient of one of these functions, f with index xi, with random index xi. And note that although we cannot compute the function value and its gradient because of these two problems, we can still compute very efficiently this stochastic gradient. So this is one example where we know that this stochastic gradient is a quite simple object which can be efficiently computed. Now let us consider another example, which again arises very frequently in machine learning, and this is called the problem of minimizing finite sums. So again, usually here this m, in the context of machine learning, this is usually the size of our data set that we have. So this is finite number, and these functions fi, they are some loss functions of our model. So x is the vector of parameters of our model, and we wish to minimize this function by taking the average on our data set. So I is the number of an object. So we want to minimize this function. This is slightly different from the previous formulation, although it is a particular case. Again, this function can be seen as an expectation of uniform distribution. So if xi is distributed uniformly, this is the previous problem. But actually, in this case, it seems possible to compute the function value. And actually, in many cases, we do exactly this. We can obtain some traditional optimization methods for solving these problems. However, the problems arise when this number of objects, the size of our data set, is very big. Indeed, to compute the function value and its gradient, we need to take this sum to compute it somehow. And for this, we need at least the order of m operations. So suppose that the data set is so big, for example, so that we are not able to compute this function even once. And this is actually possible. This is actually the case in some situations. However, again, for this problem, we can build a simple stochastic oracle. And this stochastic oracle works as follows. Given some point x, it generates a random index uniformly and returns the gradient of one of these functions. Again, if we take the expectation with respect to this random variable I0, because the distribution is uniform, we will obtain this formula. So this is unbiased. And note that the complexity of this stochastic oracle is independent of m. So we see that we can use this object even if m is very large. Now, let us consider the goals of general stochastic optimization. Let us somehow formulate this problem mathematically. Again, we want to solve this problem. We want to minimize this function. And a precise way to formulate this problem is to say that we are given some accuracy that we wish to obtain, and we wish to find some point, some approximate solution to our function, which is inside the epsilon distance from the minimum, from the true minimum that we wish to find. And note that, as we saw in previous examples, in stochastic optimization, we deal with randomness. And so all the algorithms that we use for stochastic optimization, they will generate random points. Therefore, we have this expectation here, because if we do not have this expectation, then this will be a deterministic. This must be a deterministic quantity, and of course, this is not the case. And I'll make a quick remark here, but I will not return to this in this talk. We can formulate something like this in terms of probability. So this is the way of solving the problem on average, but everything that I will talk about can be generalized to saying that we can solve the problem with high probability exactly with the same complexity. So this seems a natural goal, right? However, it should be noted that this is a natural goal only in the context of convex optimization, because it is well known that in the non-convex case, to obtain an epsilon approximate solution, even in the deterministic case, which is a particular case of stochastic optimization, this is simply not possible. This is an NP-hard problem. So when we talk about non-convex optimization, we usually restrict our attention to local minimizers instead of global minimizers, and or maybe stationary points. So we want to obtain an epsilon approximation to the gradient of our function. Now, what is the good complexity measure? For example, we want to build some optimization method that solves this problem. How we can say that one method is better than another, and so on. And it is actually quite clear when we have this notion of a stochastic oracle that the precise way to measure the complexity, a good way, would be to measure the number of stochastic gradients that we need to require from our stochastic oracle in order to obtain this epsilon approximate solution. And the main result that we will talk, that we'll discuss in the lecture is quite surprising. It turns out that a stochastic optimization problem can be solved using only epsilon to the -2nd stochastic gradients. Why is this surprising? Yes? For both goals. Yeah. So why is this surprising? First of all, we saw in the previous two examples that it simply might not be able to compute the function value. And here we are talking about solving this problem without even computing the function value. Well, this is surprising indeed. And the second reason is this. Usually, if we want to obtain, let me return, for example, to this example 1. Usually when we want to estimate such integrals, if we want to estimate them with some reasonable complexity, the most popular method for this is a kind of Monte Carlo method. We simply generate many samples and we take the average instead of this integral. And if you know what Monte Carlo methods are and how they work, you should know that Monte Carlo methods, they require epsilon to the -2nd, again the same complexity, for obtaining an epsilon approximate solution of our function value only for a single point. And here we're talking about solving this whole optimization problem with the same accuracy. So a reasonable, if you do not know the method that I will talk about in a minute, a reasonable way for you would be to, for example, to use some methods from traditional optimization, and instead of the exact function value and its gradient at every point, compute its Monte Carlo approximation, right? And if you would do that, then the complexity of solving this problem would be this epsilon to the -2nd for approximating the function value at a single point multiplied by the number of steps that your method needs to solve the problem. And it depends on epsilon also. And here again we are talking about solving this problem with the same complexity as to computing just the function value at a single point. This is quite surprising. Now let me talk about the methods that we can use to solve this stochastic optimization problem. We will start with a simple case where our function f that we're going to minimize is convex. And here we're going to consider the most general formulation that this function can be non-smooth. In a couple of slides, we'll also consider smooth convex optimization, and then we'll consider smooth non-convex optimization. So let us start with this case, and actually the main ideas are already clear in this case of convex non-smooth optimization. So again, when we are talking about convex functions, and we do not assume that they are differentiable, we usually have some substitute for ordinary gradients, which are called subgradients. Actually, this is not very important for this talk. So if you do not know what a subgradient is, do not worry. Think about this as a generalized derivative for convex functions, which coincides with the usual gradient when the function is differentiable. So the main method for solving a stochastic optimization problem is called the stochastic gradient method, usually abbreviated as SGD, and it works like this. We fix some initial point, x0, and then we repeat the following procedure. At each step, we generate a stochastic gradient of our function by calling our stochastic oracle, and then we simply try to mimic the usual gradient method. We move along the negative stochastic gradient with some constant, alpha, which is called the step size. Now, the interesting thing about this method is that if we think about the question, what should be the output of this method? Well, it seems reasonable to say that the output should be the last point, right? However, it turns out that it is not possible to obtain any guarantees for this last point, and the correct output in the context of convex optimization should be the average point on our trajectory. Now, let us discuss the convergence rate of this method. And for this, we need to introduce two main objects that will be responsible for the convergence rate of this method. And actually, this is important. The most important object, please pay attention to this, is the first one. And this constant m, this measures the magnitude of stochastic gradients. So actually, m is the square root of the second moment of our stochastic gradients. Remember that at the beginning I told you that it is not enough to assume only unbiasedness. We also need some assumptions about the fluctuations of stochastic gradient. And this is one possible assumption. In a couple of slides, I'll talk about another one. But right now, think of m as the size of a stochastic gradient. And another important quantity is, of course, the distance from the initial point to the solution. It seems reasonable that the closer the initial point x0 to the solution, the faster the method should converge. Okay, let us look now at the main result about this method. And the main result says that the output of this method, it satisfies this inequality. So let us discuss it. Here we have these two main objects, the constant m and the constant d. First of all, we have this t is the number of iterations that our method performs. First of all, let us look at the denominator. This result says us that this method converges as the square root of the number of iterations. Recall the complexity that I told you at the beginning. It was epsilon squared. So if we want to obtain epsilon approximate solution, we simply set it to epsilon. And from this equation, we see that t should be the order of epsilon to the minus second. So this is why the complexity is this. Now, we also see that the closer the initial point to the optimum, the faster the method should converge. And the most important thing, I think, for you to remember is that this constant m. Yeah. This expectation is accounting for all randomness that our stochastic oracle gives us. So our method performs many iterations. At each iteration, we generate an independent random variable, right? And then we take the expectation over the whole trajectory. This one. Well, if our initial point is deterministic, then we don't have this expectation. But if we say generate it somehow, it is also should be an expectation. So let me return to this point. From this result, we see an important thing. The smaller the size of the stochastic gradient, the faster the method converges. So ideally, if we are trying to help our method to converge faster, and we are developing a kind of stochastic oracle for this method, we should look at not only at the expectation, so that the stochastic gradient is unbiased, but also on this size of the stochastic gradient. Now let us look at the particular example to better understand this constant m. So right now it seems like this is a technical thing, but let us discuss the physical meaning of this constant. And for this, it will be convenient to consider this simple problem, which again arises in machine learning. This is again a particular case of a finite sum minimization, but here we assume that each function phi I is univariate, and our model, it simply takes the inner product between some vectors AI. In the context of machine learning, these vectors are the features of our objects, multiplied by the weights of our model. So we remember that how to build a simple stochastic gradient. For this case, we simply generate some index and return the gradient of this function, and this will be the derivative of this function multiplied by this vector. So now we're going to look at the size of this stochastic gradient at the second moment. And for this, we see that it is convenient to somehow introduce this quantity, the magnitude of our data, or the size of our data. And in order to ensure that this stochastic gradient is bounded, we also need to bound this function. So actually, this is a first assumption. In our case, we assume that this function, phi, that we have here has some bounded derivative. And if this derivative is bounded by this quantity, then it is clear that the second moment is bounded by this product of the size of this derivative multiplied by the size of the data. So our constant m, the best way to think about this as the size of the data. So the smaller the size of the data, the faster the method converges. Now let us look at particular functions phi where this assumption is true. For example, if we consider the problem of robust regression, in the robust regression this function phi is the absolute value. Actually, in the robust regression, we have some minus bi here, but it's not important. So phi is the absolute value if we consider it its derivative or a subgradient. Better say it will be the sign, and we know that this sign is bounded by 1 in absolute value, right? Now let's consider another popular application, logistic regression. In logistic regression, our function looks like this. If we compute its derivative, it will be the exponent divided by 1 plus exponent, right? And again, this is bounded by 1. For example, if we consider SVM, then by computing the derivative, we again see that this is bounded by 1, and so on. Actually, there are many examples where this assumption holds, and this G is some like a universal constant. For example, here it's also always 1. And so M is something like the size of the data. Now let us return to the convergence rate of this method. And I want to discuss the proof of this result. Actually, the proof is so simple so that it can be formulated in one slide. And this proof is useful. We will discuss it. So we want to obtain the convergence rate of our method, and for this we are going to look at the distance to the optimum. Actually, the most important property of a subgradient or a stochastic subgradient is that it decreases the distance to the optimum. So let us look at this quantity. We replace xk with the iteration of our method. This is xk minus alpha times the stochastic gradient, and now we open the square. So we simply open it, we obtain this term, now we obtain this inner product, and we obtain this gradient. And now we take the expectation. When we take the expectation of this thing, this is where we use our assumption about unbiasedness, and this thing becomes the true gradient. And here, again, why is this important? Because you already see why this magnitude of stochastic gradient matters. It already arises here. So again, we take expectation, replace it by the true gradient, and now what we do, we use convexity of our function, and the convexity says that this inner product between the gradient and the distance to the optimum is actually can be lower bounded by the function value. So we obtain this simple inequality. Now, what we do next, we take the sum. We put this term on the left-hand side, we put this term on the right-hand side, and take the sum. So we obtain this sum. Then we obtain the sum of the differences of these two things, and then we obtain the sum of these terms. And now we use a very important property. Note that this sum can be simplified because this sum telescopes, and we only have the first point, the initial point, minus the last point here. And we leave this sum as is. So actually what we obtain here, we obtain some bound on the sum of our residuals in terms of the objective functions. Now let us divide this by t. And when we divide this by t, we simply drop this term because it's negative. This is d squared, this distance to the optimum. Here we divided it by t. And then we replace the size of our stochastic gradients by this constant m. And why I discuss it? Because from this proof, you can see why we return the average point and not the last point, for example. Because we can obtain the guarantee only for this expected error in terms of our objective function. And when our function is convex and x is the average point, we know that the function at the average point is not bigger than the averages of these things. Now, let us look at this result, what we obtain here. Actually, it is very interesting. We obtain here the sum of two terms. The first term goes to 0 as 1 divided by t, quite fast, faster than 1 divided by square root of t. But the second term, it does not depend on t. And so this is something like deterministic part, which goes to 0, and this is the noise. Recall that m is the size of our stochastic gradients, and when m is big, this noise is big. And from this we see that in order to ensure the best convergence of our method, we need to choose the step size appropriately. And a good way to do this, if we know this, right, would be to minimize this, to set alpha to some value which minimizes these two expressions. And when we have something divided by alpha plus something linear in alpha, it is clear that the best alpha will be the one that balances these two terms. So we need this term to be equal to this term, because if this term is small, this will be very big. When this is small, this will, okay, you understand. So when we choose this alpha, which actually balances these two things, or which minimizes this expression, we obtain this, and it turns out that the best alpha should be proportional to the square root of t. That's why we obtain this square root of t dependency. This will be important later in the second part of our talk, where we will talk about how we can reduce the noise and to obtain faster methods for solving a particular case of a stochastic optimization problem. Okay. Let us summarize this. The basic SGD method obtains this convergence rate. Now, let us consider another situation. Before we considered non-smooth functions, now let us consider what happens if our function is smooth. Maybe this SGD method will accelerate or something like this. So the question is, what happens when our function is smooth? Actually, we will see that the basic SGD method does not accelerate, and actually it is possible to prove, but we will not consider this in this lecture, that this rate is optimal for general stochastic optimization. It means that by having access only to stochastic gradients, it is not possible to build any method that will solve our problem faster than epsilon to the minus second iterations, even if our function is smooth. But for special kinds of problems which we will consider in the second part of this talk, it will be possible. So let us again look at smooth problems. And smoothness in optimization, it doesn't simply mean that our function is differentiable. We need to require something more from this. And usually this is formulated as the notion of an L-smooth function, it is depicted in this picture. So we say formally that our function is L-smooth, first of all, if it's differentiable, but L-smoothness means that our function at any point can be upper bounded by a simple quadratic function. Actually, this is not related to convexity, this is independent, so our function f may be even non-convex, but what we require that it does not oscillate like this. So it is smooth, and this means that at any point we should be able to upper bound our function by some simple quadratic function with some constant L. And this constant L turns out to be quite important. So a sufficient condition for this, it is quite simple. We see that this is the first order Taylor approximation of our function, and if we consider the second order Taylor approximation for our function, and if our Hessian, if our function is twice differentiable and its second derivative is uniformly bounded by this constant L, then this will be true. What? Yes, it is not Laplacian. This condition is actually related to something which is called Lipschitzness of the gradient of our function. So if the gradient of our function is Lipschitz, then again, this will be a sufficient condition for this to hold. Let us look again at an example to keep things concrete, to again better understand the physical meaning. And again, it turns out that this constant L is related somehow to the size of the data. Again, let us return to our simple example, empirical risk minimization, where our function has this form. Let us compute its second derivative. Its second derivative is given by this, right? The second derivative of this function multiplied by this simple rank 1 matrix, A transpose. And in order for this quantity to be uniformly bounded above, we need to uniformly bound the second derivative, and we will again obtain the size of the data, right? So this B, again, the size of the data, we have B squared here, and the size of this derivative. And again, in many cases, this is true that many functions have bounded second derivative. For example, in least squares, when our function is quadratic, if we compute the second derivative, it will be bounded by 1. Again, in logistic regression, we computed the first derivative, but we can also compute the second derivative. And we can see that it is easy to see that it is bounded by 1, but actually by something smaller. Okay, let me mention quite important fact. It will not be needed in a moment, but we will return to this in the second part. It will be important. So again, let me recall to you that this is independent of convexity, this notion of L-smoothness. However, if our function is L-smooth and additionally convex, then we can say something interesting about this function. Let us look at the picture. So what this inequality says. We know that if the function is convex, it means that at any point we draw the tangent line and our function lies above this tangent line. What this inequality says, so if we remove this term, then this will be the definition of the convexity. Function lies above the tangent line. However, if our function is additionally smooth, then it means that this this distance between our function and this tangent line, lower support of our function, grows at least as this quantity. Just remember this picture for now, and we will return to this. Actually, this fact will help us to reduce the noise of our stochastic gradient in the second part of this lecture. Now, let us talk about another assumption. Previously, we talked about the magnitude of stochastic gradients, and actually there is another way to measure the fluctuations of stochastic gradients, which is useful in many applications. And this is based, maybe I would say this is more natural, even more natural than the first assumption. This is based on the variance. Right? It seems natural to require this assumption, that if we want to measure somehow the fluctuation of our stochastic gradient, and we know that the expectation of g of x equals this, then a standard thing to require that the variance is bounded. Actually, this leads to a slightly different assumption, and let us discuss how these two assumptions are related. Actually, we know this is a standard thing in probability. I think that the variance equals the second moment. So if we open the square, the intermediate term will cancel, and we will obtain this expression. So the variance equals the second moment minus the squared norm of the true gradient. And it shows that this constant sigma is always, at least, is always smaller than this constant m. So if we know that the size of our stochastic gradient is bounded, then we know that the variance is bounded. However, there are some applications where it is useful to consider variance. The first thing, this is just some simple example, but we will return to a more interesting example in a couple of slides. Let us consider, for example, that we compute the stochastic gradient with some error, right? What we do, this error is 0 in mean, and the second moment of this psi is bounded. This means that the variance of our stochastic gradient is exactly bounded by this sigma. However, let us look at the constant m. Recall that the constant m, we wish for this to be very small, because the smaller m is, the faster the method converges. And here, let us compute m. M is the second moment of our stochastic gradient. And again, if we open the square, here, so we plug this g, we use the fact that the expectation of psi equals 0, this cancels the intermediate term, and we obtain this expression. And we see that the second moment is actually maybe much bigger. This is sigma squared, this variance plus the size of the gradient. And if the gradients, the true gradients in our problems are very large, they may be, in fact, even unbounded. So this second moment may be arbitrarily large, and what we talked about previously, it may simply not work. However, if the variance is bounded, we will see that, just a moment, we will see that this is a reasonable assumption, and the same method as GD, it can work also when our variance is bounded, and we will obtain a similar guarantee, but with m replaced by sigma. Yes, your question? Okay. And the second example, which is used quite frequently in practice, is related to mini-batching, and we will return to this in a couple of slides. Now, let us talk about the same method that we talked about previously, but now we assume that our function not only convex, but smooth. Does it give us anything different? Well, yes and no. As I already said, we will see that the epsilon to the minus second power complexity cannot be improved. However, we will be able to replace this constant m by sigma, and in many cases it is useful. So actually we consider exactly the same method, which computes the stochastic gradient and moves along the negative stochastic gradient. Again, we saw that in the context of convex optimization, we need to output the average point in our trajectory. And the result about this method, it says us something very similar to what we had before. But now, actually, we have two terms here. But from the proof of the SGD for non-smooth convex optimization, we also saw that we had two terms there as well. So let us look at these two terms separately. This term, again, scales as 1 divided by t, so it converges quite fast. And this term is related to noise, because we have this constant sigma. Sigma is the variance. Recall that in the previous case, we also had this 1 divided by square root of t dependency for noise. And here we see that although we have two terms, one converges fast, this converges slower, because of this noise, we cannot be better than 1 divided by square root of t. And this again gives us the same complexity. But this result is slightly different, because we have this constant sigma. For example, if sigma equals 0, what it means that we use exact gradients for minimizing our function instead of stochastic gradients. And actually, our method, this one, becomes the standard gradient descent method. And this result says that the standard gradient descent method converges faster, right? Than SGD, it converges as 1 divided by t. So actually, this is convergence of the standard gradient descent method, and this is noise. And we see that this constant sigma should be small for this method to be effective. Again, previous result was like this, and we saw the same complexity, still epsilon to the -2. So to summarize, it turns out that this complexity cannot be improved. I already told you about this, even if our function is smooth. It changes things slightly. It replaces this constant m with constant sigma, and we saw that in some contexts this sigma can be quite small, but in terms of the dependency on epsilon, we cannot improve anything. Yeah. Well, they are independent. They are independent. So I will not go into discuss this proof, but again, it uses all these same ideas. We need to somehow look at this distance, open this distance, and use convexity, then take the sum, and so on. And actually, this is very similar, so let me skip it. Now, let me call about a very useful concept that I already mentioned, which is called mini-batching. Actually, when we consider the variance of stochastic gradients, this allows us to talk about this mini-batching. And this is a simple idea that says that let us modify our stochastic oracle. Instead of returning the one stochastic gradient that we had previously, let us call the stochastic oracle big N times, obtain these independent stochastic estimates of our true gradient, and simply set return the average of these stochastic gradients. And this is usually very efficient when we can compute these stochastic gradients in parallel. So if we have big N number of processors or workers, we can basically compute this quantity in the same time that we computed just one of these stochastic gradients. So in terms of the complexity for generating stochastic gradients, if we have parallelism, this is the same. However, we may hope that by taking n very large, this will decrease the variance and accelerate the method. And knowing the previous result, we know what quantity we should estimate. And actually, again, this is a standard result in classical probability and statistics, is that the variance of this thing, if these GI are independent, it actually will be n times smaller. So the proof is quite simple. We simply open the square. We have these two sums, and because these GI are independent, we can plug the expectation inside, and this cross term cancels. We obtain this, and the variance will be n times smaller. And for us, it is useful because we know this bound. We know how our SGD method converges in terms of the variance. And we know that if we decrease sigma squared in n times, it means that sigma is decreased by square root of n times. Which means that if we take, for example, 100 processors, then we can actually accelerate our process in 10 times. Not 100 times, as you may suppose if you do not compute these things exactly, but it turns out that the dependency is square root. So it means that because the square root grows much slower than the just n, it means that usually it makes no sense to pick this n large. But if you have n processors, you can actually take n equal to the number of processors. Now, yeah. This slide? This one? This one? Yeah, yeah. Yeah, that yeah, okay. That is a useful remark. Actually, from this we can see that it also makes no sense to pick, for example, very large mini batches, because if sigma is if n will be greater than this number t, right? This will become 1 divided by t as well. Because we have this term, we cannot be faster than this, and so it means that again sigma n should not be very large. But anyhow, let us consider now the last topic for general stochastic optimization, and the last topic will be about, now we consider non-convex functions. Previously we considered convex both non-smooth functions and smooth functions. Now we consider non-convex functions, and we make again the same assumption that our function is smooth, so that we can talk about gradients, but now it may be non-convex. Remember that in the context of non-convex optimization, we actually cannot ensure anything in terms of the function values, but we can ensure something in terms of the gradients. And it turns out that in the context of non-convex optimization, although we have a similar process here, this SGD method as before requires stochastic gradient, move along the negative gradient, our output should be different. Recall that in the context of convex optimization, we returned the average point on our trajectory, right? Now, in the context of non-convex optimization, this idea seems to be bad, right? Because if we have a non-convex function, then to average the whole trajectory will give us something inappropriate. And here it turns out that what we should do instead, we should return just the random point on our trajectory. So actually this is formulated in this way, but this algorithm actually should be, if one implements this algorithm, this should be organized slightly differently. First of all, we generate some uniformly distributed number between 0 and t. We decide how many iterations we wish to perform. And then we do not perform all the iterations, but we perform only only that number of random iterations that we need. And actually note that this is not very strange, because when we generate the number of iterations that we wish to perform uniformly, the expectation of this number of iterations will be t divided by 2. So actually, on average, we perform the same number of iterations. We do not return this point randomly because we want to reduce the number of iterations of our method, because it will be the same. T or t divided by 2 doesn't matter. We return the random point because we cannot guarantee anything for the average point, and we cannot guarantee anything for the last point. It should be again the random point. Again, let us look at the convergence rate of this method and recall that now this convergence rate should be formulated in terms of the expected gradient of our function. We want to reduce the gradient as fast as possible. And it turns out that if we look at the gradient squared, then we obtain exactly the same result as we had before for convex optimization. But the only difference here is that previously we had d. The d was the distance from the initial point to the solution. Now we have the distance in terms of the function value, but these things are almost the same. What matters is that the result is almost the same. It's exactly actually the same. And we have two terms here. One is deterministic, which converges quite fast, and the second is stochastic, which converges as 1 divided by square root of t. And again, we have this important quantity sigma here, which is the variance of our stochastic gradients, and we wish this variance to be as small as possible in order for this method to converge as fast as possible. Again, it is interesting to look at the case where sigma equals 0, because it gives us the classical gradient descent method, and as a byproduct of this result, we obtain the convergence rate of the classical gradient method for non-convex case, and again, it is faster. It is not square root of t, it is just 1 divided by t. And actually, you may wonder why we have two different methods for convex optimization, for non-convex optimization. It should be the right thing for this. It should be just one method, right? In the context of convex optimization, we return the average point. Here we return the uniform point. But it turns out that this method is, I would say, is more correct than the previous one if we do not want to assume anything, if we do not know that our function is convex or non-convex, because if we look at the at this point, which is generated randomly, we obtain the same guarantee for the convex optimization. So if our function is convex, then the same point, not the average point, but this random point, it gives us the same guarantee. So actually, the best thing is to use this approach if you do not know anything about convexity. Now, I think we have some time, right? And this proof is slightly different than the previous proof, and it uses L smoothness. Let us look at this. It is again quite simple, but we will see what happens here. So recall that L smoothness means that we can upper bound our function above by this simple quadratic function. And in the previous proof, actually, we looked at the distance to the optimum. And I said that the most important property of a stochastic gradient is that by moving along the negative stochastic gradient, we reduce the expected distance to the optimum. In the context of non-convex optimization, we cannot reduce the distance to the optimum because it is NP-hard, but we can reduce efficiently the function value by moving along the negative gradient. If we move along the negative stochastic gradient, we reduce the expected value of our function. So here we look at the function value, apply this L smoothness. Now we use the definition of the iteration of our method, xk plus 1 equals xk minus alpha gk. So we obtain this term here, and again we obtain this thing here. Now we take the expectation of gk equals the true gradient. So this term becomes this. And now what we do, we introduce this delta k. This is actually the error in estimating the true gradient. And we add and subtract delta k here and open this square. So we obtain this thing. Again, by moving expectation inside, this term cancels because the expectation of delta k is 0, right? And we obtain this term, which we combine with this thing, and we obtain a slightly different coefficient here. And this is where this variance comes into play. Because we have the expected norm of delta k here, and we know that the expected norm of delta k is exactly our constant sigma, our variance. So this looks actually quite, this approach is very similar to what we did before, but just slightly different. Now, when we have this, we perform the same trick as before. We move this term on the left-hand side, this term on the right-hand side, and take the sum. And we obtain that this inequality. When we move this on the left-hand side and divide by this, we obtain this telescopic sum of the differences between function values, and we obtain actually the same term. And let us discuss why we generate our output randomly, uniformly. Recall that in the context of convex optimization, we had a very similar situation, but here, instead of taking the sum of the gradients, we took the sum of the of the errors in function. And we use convexity. Now we cannot use any convexity, but if we say that this output of our method yt is a uniform, is chosen uniformly at random from these points, right? By the definition of the expectation, what it means that this expectation equals 1 divided by t. This is uniform distribution, and this sum. So we have this term here. And we obtain this result, and again, by choosing the best alpha, we obtain what I already mentioned in the previous slide. So this concludes the first part of this lecture. Does anyone have any questions about general stochastic optimization? Okay. Now we move to, yeah. Yeah. No, actually, it is a very good question, and there are some results that can provide us with guarantees for the final point, but for this we need additional assumptions. So theoretically, by making only the assumption about the variance or the magnitude of stochastic gradients, we should return the random point on our trajectory. But if our function is better somehow, if we have some additional structure in our function, then in some cases it is possible to return the last point. And actually this is the case for strongly convex optimization when our function is strongly convex. But again, let me not discuss it in detail. So the second part will be about beta methods for stochastic optimization. Actually, we already discussed that for general stochastic optimization, when we have access only to stochastic gradients, it is not possible to improve the epsilon to the -2nd complexity. For example, if we want to obtain 1% accuracy in our optimization, we need somehow something similar to 10,000 iterations of our methods. This is quite large, and ideally we also want to improve the dependency on this epsilon. For example, can we make something similar to the classical gradient descent? Because the classical gradient descent, it converged as 1 divided by t, which means that its complexity is epsilon to the -1st. And if we want to obtain 1% accuracy, this means that we need to perform 100 iterations instead of 10,000. So this is much better. But I already said that the complexity of the classical SGD method is unimprovable if we do not have any additional structure inside our function. However, it is improvable if we consider some special functions. And it is interesting to consider the finite sum functions that we talked about at the beginning. Recall where our function f is the average. So when we are solving, for example, machine learning problems with a finite data set, we have these kinds of functions. So this is also very important. Now let us talk about the complexity measure for this problem. What is the right complexity measure? Recall that for the general stochastic optimization problem, the right complexity measure was the number of stochastic gradients we needed, because we assume that to require a stochastic gradient is some basic operation, some simple operation, and we wish to compute the number of such operations. The natural question here is what should be a natural measure, complexity measure for this problem. And again, it is quite obvious. We saw it at one of the first slides. When for these problems, if we generate stochastic gradients, it means that we pick one index, I, uniformly at random and return the gradient of this function. So the right complexity measure for these problems will be the number of computations of individual functions Fi, because usually these functions are simple and this function is complex because we need to take this sum. Now let us discuss this table. Let us consider two methods that we already talked about, the classical gradient method and the SGD method for stochastic optimization. Let's start with the classical gradient method. We saw that for the both convex and non-convex optimization, it was a byproduct of our analysis for SGD when the variance is 0. This method has dependency as epsilon to the minus first. So it's better than epsilon to the minus second of SGD. However, recall that each step of this gradient method, it requires to computing the gradient of this function f. And to computing the gradient, we need at least m operations. So it means that the overall number of computations of these individual functions is m divided by epsilon. If we compare it to the SGD method that we talked about previously, then we know that it has its dependency on epsilon is worse. It needs epsilon to the minus second iterations. However, this method, it does not depend on m at all. And this was the reason why we considered this method when m was very big. Each iteration of this method, it requires computing just one of these individual functions, and so we do not have any dependency on m at all. The question is, can we somehow combine these two approaches? Can we obtain the epsilon to the minus first dependency by utilizing this problem structure? And actually, it turns out that this is possible, and this leads us to a special algorithm for solving these kinds of problems, which is called SVRG. And it is based on the idea of variance reduction. So SVRG stands for Stochastic Variance Reduced Gradient Method. Let us look at this row. We see that for example, for convex optimization, this method needs epsilon to the minus first power of iterations. This is exactly this, but without m. And however, we do not achieve this for free. We pay for this by this factor m. And note the dependency on m. Here, this is very moderate. We have logarithm here, and the logarithm usually is a very small number. This function almost does not grow. For example, logarithm of epsilon for any reasonable accuracy epsilon we wish to obtain is something like 5 or 10. And what this means that actually the complexity of this method, we need to somehow compute this function f or its gradient 1, 2, or 5 times, say, and then we simply pay this epsilon to the minus first complexity. So if m is very big, this is just not possible, the usual gradient descent. However, if m is not that big so that we can compute this function value and its gradient at least once, then we can use this algorithm. And it is also more efficient in the context of non-convex optimization as well. So to talk about this algorithm, let me return to this bound, which we had for the classical SGD method. Actually, this SVRG method can be seen as some clever improvement of the ordinary SGD method, and it is based on this method. The ordinary SGD method, we saw that, for example, for the simplest, let us again first consider convex optimization. It had two terms here. The first term was deterministic, which decreased as 1 divided by t, and the second term was responsible for the noise. And again, I return to the assumption about the magnitude of stochastic gradient. This can also be formulated in terms of the variances as well. So we see that to obtain epsilon to the minus first complexity, which is the same as 2 to require that this thing converges as 1 divided by t, we need somehow this m to be small, ideally 0, right? For example, let us consider the classical gradient method. And in the classical gradient method, this gk equals the gradient. And we know that the expectation of this gk, this is simply the norm of the gradient. And we know that if we optimize our function in the right way, it means that this xk somehow converges to the solution, then the gradient must go to 0. And it means that after some time, this constant m will decrease, and eventually it will go to 0, and eventually we will obtain this 1 divided by t convergence rate. So this is just some idea, but we will now see how this is actually implemented. And the main question, of course, is how to ensure the same thing, that the magnitude of our stochastic gradient goes to 0 in the presence of noise, when we do not have exact gradients, but we have only stochastic gradients. How to do this? And actually, it's a very interesting idea. It's the key idea behind the SVIG method, but it is also I think it is very important because it is actually a general idea that can be applied not only inside this SVIG method, but actually in many different situations as well. So let us look at the finite sum problem and recall that usually previously we used the gradient of one individual function as a stochastic gradient, and it was an unbiased estimate and so on. However, we saw, for example, for empirical risk minimization, that the magnitude of this thing, it does not go to 0. It is related to the size of the data, and there is no way it can go to 0. So what we do here, we add some additional term, which will be 0 in expectation. And this is the difference of these two gradients. The first one is the full gradient of our function, and the second is exactly the gradient of the same function, but these two gradients are computed at a different point. So this was point x, and we somehow fixed, before we compute this g of x, we somehow fixed this x tilde, which is called the reference point, and we add this simple term here. If we compute the expectation of this term, it is 0, because the expectation of this thing equals this, and this is deterministic. So from the point of view of unbiasedness, it's exactly the same. However, its magnitude will go to 0, and this is shown in this key lemma. We will prove it in a minute. It is very simple. The proof will be here. So what this lemma says us, it says that if these functions are convex and smooth, then the error in estimating, not the error, the magnitude of the stochastic gradient can be bounded by this thing. Let us look at this expression. It has two terms here, and both terms are of the type the error in estimating the function. So we see that when our method converges, eventually, if it minimizes our function appropriately, this term converges to 0, and this term converges to 0. So it means that in order to use this idea, and the idea is to replace the simple stochastic gradient which we used previously by this expression, we actually need from time to time to move these reference points along the trajectory of our method. So this, if we fix this reference point, then this thing will not go to 0. But if we move them along with our method, then we obtain something useful. And let us look at the proof. The proof is very simple and very instructive. As I said, this idea can be applied not only in the context of this SVIG method, and maybe even not in the context of optimization as well. So we look at the quantity at the size of the stochastic gradient. We wish to be small as possible. Let us plug this expression here. So we just replace g with its definition. It is this expression. And now what we do, we add and subtract the gradient of this individual function at the solution. So if we add and subtract and use this inequality that the u plus v squared is less than this thing, what we obtain is we obtain this. So we subtracted here this, used this inequality, and then we also added this thing here. And what we also did, we added this thing. Note that this is 0 because the gradient of the whole function at the solution is 0. So we obtain this thing. And note that this is a very interesting expression because this is exactly the expectation of this. So this is the variance of this thing. And we know that the variance can be upper bounded by the second moment. We already talked about this. So what we can do, we can simply drop these two terms and we obtain this thing. And now what we use the important fact that I talked about when we discussed smooth functions. Recall that when our function is smooth and convex, then this distance is greater or equal than the difference between the gradients. And here we have the difference between the gradients. So what we do, we use this inequality. We know that the difference between the gradients, it can actually be upper bounded by the function value, this minus the lower support which comes from the first order Taylor approximation. So we have this. And also we have the same for the second term. And when we compute finally this expectation, these two cross terms, they disappear, and what we obtain, we simply obtain this result. So it's a very simple proof, but it shows us that by this interesting idea, we can actually reduce the magnitude of the gradients to 0. And recall that if we can reduce the second moment, this means that we can also reduce the variance, because the variance is always smaller than the second moment. So this is actually, this result actually implies that the variance of this thing also goes to 0. The variance and the second moment, they both go to 0. Now, what is this SVIG method? Actually, it is quite simple. Let me show it to you. What we do here, we perform, this looks very similar to the classical SGD method, but now we have two loops here. Previously, we had only one loop over the iterations, and this was our previous SGD method. Now what we do, first of all, we add the outer loop, which goes to some number, and this S is usually called an epoch. Epoch means that we process for each outer iteration. It means that we process all these m functions. We compute them all. What we do here in each outer iteration, first of all, we compute the gradient of the full function at the reference point, and for this we need to compute this sum explicitly somehow. So this is a complex operation, but note that it is performed only in the outer loop. And then we perform inner iterations. Inside inner iterations, we do the usual SGD method, but with this stochastic gradient which comes from the previous slide. We add the full gradient at the reference point and we subtract it. Remember from the previous slide that we saw that in order for this process to be effective, we need to move these reference points x tilde from time to time. And this is what we do at the end of this outer loop. It turns out that we need to set them to some values. Again, it is not very important that what we have here exactly. It is important that these reference points, they somehow move with these points of our method. So this is a two-loop method, and at the end we simply return the last reference point that we compute. let us look at the complexity of this method, because it's slightly different from the classical SGD method, because we have two kinds of operations here. The first operation is very expensive. It's the computation of the whole gradient. And the second operation is very cheap. It's the computation of the just stochastic gradient for one individual function. So the whole complexity, and recall that the complexity means the total number of computations of these individual functions. It is, let us look at this. It is this sum. So we take the sum over epochs, over S, and then at every iteration of the inner loop, we compute just once this function fi. So we have this sum here. But also we have to check, we have to take into account this operation. At every epoch, and we have biggest number of epochs, we compute m times these individual functions. And so this gives us this total complexity. And from this we see that we should not have too many epochs, because if we have a lot of epochs, then this will be simply very big, this complexity, right? M multiplied by something big. However, it turns out that it is enough to perform only a logarithmic number of epochs. And recall that the logarithm is a function that does not grow. So usually this quantity may be replaced by something like 10 or 20, I don't know. And it means that we should compute the whole gradient only some fixed number of times, say 10 or 20. But inside the inner loop, we compute these quantities many times. And so the result about this SVG method, it tells us this complexity. So again, we replace S by the logarithm. This is a very small function. And it turns out that this sum, the sum of the sizes of inner iterations, it grows like this. So this is, I recall you, the complexity of the standard gradient method. So it turns out that this SVG method basically gives us the same speed as the gradient method, but each iteration of this method is m times cheaper. And so it is applicable for these kinds of problems, even if m is very large, when the gradient method is not applicable. And again, to summarize what we obtained the improved convergence rate, epsilon to the minus first instead of the epsilon to the minus second. Now, again, let me not discuss this proof in a detail. If you are interested, you can look at it yourself. Just, I will just briefly mention. We use the previous result from the SGD method that we had. Actually, this proof is based on the proof of the SGD method that we considered before. If you take the result of that proof, you remember that we had the sum of the magnitudes of this GK, and when we apply the key lemma, we can actually replace this GK by the function values, and again perform the same trick, taking the sums and so on. And the proof is very simple. That is it, actually. And in the previous slide, we talked about convex optimization. Actually, this method SVG can be generalized to non-convex optimization as well. It is exactly the same method, but we need to choose the reference points slightly differently. And actually, coming back to the question of what we should return, the average or the last iterate and so on. For example, for this method SVG, for non-convex optimization, it makes sense to return always just the last iteration as the reference point. However, the output should be again chosen uniformly from the whole trajectory as in the usual SGD method. And again, even in the context of non-convex optimization, we may actually outperform the basic SGD method because we have this epsilon to the minus first complexity. Okay. Now, this was all theory. Actually, these are some practical results from applying the method from the previous slide, the SVRG method for non-convex optimization. And actually, in many situations, as you can see from these plots, SVRG method really works faster than the SGD method even for non-convex problems such as optimizing neural networks. Well, that's it. Let me conclude and summarize this lecture. In the first part, we discussed the general stochastic optimization. The main idea of the general stochastic optimization is to replace the exact gradient with some stochastic approximation of this quantity, and it should be unbiased. It's the main property. The main method, the most important method for stochastic optimization, is the SGD method that we talked about. And for solving the problem with epsilon accuracy, we saw that it requires epsilon to the -2 computations of stochastic gradient. And do not forget that actually, although this complexity is formulated like this, we have some hidden factors inside this complexity. And these factors are very important. The most important characteristic that we can control is the variance of stochastic gradients or the magnitude of stochastic gradients. So if we wish to design a stochastic oracle, and we wish to help this SGD method to converge fast and so on, we need to look at these quantities. And we need to design such stochastic gradients so that these quantities, either m or sigma, are as small as possible. And if we consider the special case of the general stochastic optimization problem, which is called the minimization of finite sums, we saw that these m and sigma, these two quantities, they can be efficiently reduced dynamically, and this led us to the SVRG method that had this improved dependency on the accuracy that we wish to obtain. However, let me point out the difference between this SVRG method and SGD method, because you may think that if we optimize these finite sums, then we should always use this SVRG method. Actually, this is not the case, and the answer is that we can use this SVRG method if this parameter m is not very large. And not very large, it means that we are able to compute this function and its gradient at least one time. So remember that, in the SVRG method, we somehow modify the stochastic gradient by using the true gradient of this function, and we computed it exactly. If we are not able to perform this operation, if this m, the size of the data set, is so big so that we cannot even compute this function value once, then we cannot use SVRG, and the only thing that we can do is to use this method. However, if m is not that large, it may be still large, but not too large, and we can compute the objective, we saw that it needs to be computed something like 10 or 20 times. If we can do this, then it is actually a very good idea to use this SVRG method. That's all. If you have any questions, we have 5 minutes. Yeah. Okay, the question was, let me return to this. It's about SGD method, right? Okay, let me first, the question was how to choose the step sizes in these methods, because let me, for example, look at the SVRG method. So this SVRG method, it uses some step size alpha, and actually the theory tells us that this alpha should be chosen to something like 1 divided by L. And L is the smoothness constant of our objective function. So if we know this constant, then yes, we can use this value of alpha. However, we do not know it in many cases, and this is a good remark. So actually, this is a problem for all stochastic optimization methods, that very often, indeed, we do not know some characteristics of our objective function, even if they exist, like this L. And so what we should do, we should somehow try different values for this parameter, try different constants for alpha, and choose the one that works the best. Yes. Here, this number of iterations. Yes, I understand. These are all good questions. Actually, this is theory. The theory says that if we know these quantities like this delta, d, and so on, then we should choose all the parameters like this. Of course, in practice, we often do not know many quantities, especially this one, once the distance to the solution and so on. And yes, this is indeed a problem. And this problem is usually resolved by trying different values for these parameters. And the unfortunate news is that there are no automatic procedures that can choose it for you. So this is a problem, and this is an intrinsic difficulty, I would say, of stochastic optimization. Yes? Yes. This thing, you mean? This is kind of constant, yes. You mean this term, right? But actually this term... okay, I understand. If you look at the result for the SGD method, then it has m times d divided by epsilon squared. M squared times d squared divided by epsilon squared number of iterations. So actually, if you look at the precise constants, then this is actually comparable to the constant inside the SGD method. And in the denominator, things are better because we have epsilon instead of epsilon squared. So the short answer to your question is that if you look carefully to the complexity of this SVG method and to the complexity of the SGD method, you will see that the SVG method is always better, even up to some constants. This term. Well, yes, but as I said, if you assume that you can compute your objective like you mean that this can be larger than this, right? And so this dominates the cost. Okay, sorry. Let us return to this after the lecture. Yes. Okay, if I understood the question correctly, it was about that we talked just about optimizing a function, and usually if we consider machine learning problems or statistics problems, then this optimization is just an auxiliary, some auxiliary problem, and our goal is to not achieve some epsilon approximate solution to this problem, but to achieve some guarantees, statistical guarantees in terms of the expected risk, generalization error, and so on, right? So the answer to this is that yes, indeed, I considered only the optimization part of the whole story, and actually there are many works that indeed use this all this theory inside to obtain statistical guarantees as well. For example, it is well known that for least squares problems, the classical, not maybe classical, but the SGD method with some appropriate step sizes and so on, it converges to the optimal estimator from the statistical point of view in terms of the Fisher matrix and so on. So there exist a lot of results about this method, but they are simply beyond the scope of this talk. Let me talk to you about this question after the lecture. Okay, last question, and we will finish. The question was, what is the dependence of the complexity for solving our stochastic optimization problem and the number of variables n that we have here. And actually the answer is if we only calculate the number of calculations of these individual functions, then there is no dependency at all. However, the dependency on n lies inside the stochastic oracle. For example, let me just briefly return to this problem. Just a moment. For example, if we consider this empirical risk minimization, here is the stochastic oracle, and to compute the gradient, we need to compute this inner product, and this inner product takes n operations. So in many cases, it is something like the number of variables, the complexity of the oracle. Well, that's it. If you have any additional questions, please feel free to ask me at the coffee break or something like this. Now that's all. Thank you.